Okay, so welcome to mathematics class, and we were talking about quadrilaterals. So let us continue from where we had stopped. So in the last class we had a brief introduction about what are quadrilaterals. Then we talked about the angle sum of quadrilateral, right? The sum of all the angles of the quadrilateral. And then we talked about different types of quadrilaterals, right? We talked about squares, rectangles, kite, parallelogram, rhombus and trapezium. And then we were talking about the characteristics of parallelogram, right? We were talking about different theorems based on parallelograms. In this class we will continue with the topic, and then we will look at another condition for a quadrilateral to be a parallelogram. And finally we will look at the midpoint theorem. So let us continue from the question where we had stopped, right? We had asked you this question: two parallel lines L and M are intersected by a transversal P as shown in the figure. Show that the quadrilateral formed by the bisectors of the interior angles is a rectangle. I hope you have tried to solve this question, and in this class we will show you how to solve this question in a very easy way using whatever we have learned so far. So let us start off by drawing the diagrams according to the question given. So we need to draw the angle bisectors first, right? So let us draw the angle bisectors of this angle and this angle. Let us draw them. So let us now draw the angle bisectors from the vertex C also. So you can see we have drawn all the angle bisectors, and you can see the two angle bisectors on the left side of the transversal P meets at B, and on the right side they meet at D, right? So according to the question we have to show the quadrilateral formed here ABCD is a rectangle, right? We have to show the quadrilateral formed by these angle bisectors, which is ABCD, is a rectangle. So let us see how to solve this. So let us make more space here. So let us start off by naming these angles, by taking some specific values or some variables for these angles so that we can calculate them easily. So we have taken angle PAC, which is this one. Angle PAC we have taken as twice x. And why have we taken it? Because ultimately we have to evaluate the values for the angle bisectors, right? So the value of angle bisector will be x, and that is why we have taken the entire value of the angle as 2x, so that we don't get any fractional kind of equation. So we have taken angle PAC as 2x, angle SAC, which is this one, angle SAC is this one, right? Angle SAC we have taken as 2y. So we have named these two angles. Now we don't need to write angle PAC or angle SAC over and over again. We can write x, we can write 2x or 2y whenever we need them. So you can see, if this angle is 2x, obviously angle ACR will also be 2x. And why is this? They are alternate angles, right? Because L is parallel to M, and then P is a transversal, right? So you can see these two angles are alternate angles. And also for the 2y part, so we have taken angle ACQ also as 2y. Angle ACQ, which is this one, right? Angle ACQ we have taken as 2y. And why is that? Because this angle, angle SAC, was 2y, right? And so this angle is an alternate angles, and in a similar fashion as we had found out 2x. So you have got the name for all these angles, and very easily you can find out the values in terms of the variables x and y for the angle bisectors also. So you can see the measure of the angle bisectors are half of them, which is x and y, right? So this angle and this angle measures x. Also this angle and this angle measures x individually, right? All these angles measure x individually, because this angle, this whole angle was 2x. This whole angle, which is an alternate angle, was also 2x. Similarly, we can also find out the value for y, and you can see we have specifically written the angles which we need. Angle BAC, which is this one, right? We need the interior angles, and we need actually these angles which constitute the quadrilateral ABCD, right? So we are concerned with only those angle bisectors, or those bisected angles which are inside this quadrilateral. So angle BAC and angle ACD are x, and now what we do, you can see here, as these two are x, and we will talk about y a bit later, because it will happen in a similar fashion. You will see, as you can see, this angle is equal to this angle, right? And can you observe something? The upper angle is made by the transversal P with the line, with the ray AB, and the bottom angle is made by the transversal and the line CD, right? So they are acting as an alternate angle, right? They are acting as an alternate angle, and if we have alternate angles and both of them are equal, we can say that the lines which are making them are parallel to each other. Hence we get AB is parallel to CD. So you can see we have got two alternate angles which we have got from the angle bisectors. These two angles are equal and acting as alternate angles, and therefore we get AB parallel to CD. And now similarly, if you see angle ACB, which is this one, and angle CAD, which is this one, these two are equal, and you can see if the transversal is P, then the rays are CB and AD, right? So these two also must be parallel to each other, right, by the same rule. So we have got AB parallel to CD and CB parallel to AD, or we have got this side parallel to this side, and separately this side is parallel to this side. So can you see that we have actually found out that ABCD is actually a parallelogram, right? One step has completed. We have found out one of the characteristics of a rectangle, that it is a parallelogram, right? And to find out it is actually a rectangle, we have to prove that all the angles are 90 degrees, right? So let us move forward. So we have found out ABCD is a parallelogram, right? So let us find out the measures of angles. Angle PAC, which is this angle, and angle ACQ, which is this angle, add up to 180 degrees. And why is that? You can see both of them are co-interior angles, right? Where P is the transversal and L is parallel to M, right? Both these angles are acting as co-interior angles. They are on the same side of the transversal, and both of them lie in the interior region of the parallel lines. So both of them add up to 180 degrees, right? So 2x plus 2y, which is the measure of these two angles, 2x plus 2y, both of them add up to give 180 degrees, right? We have just replaced those angles by the variables. So if twice of x plus twice of y gives 180 degree, so x plus y will give out half of it, right? Twice of x plus y gives us 180 degrees, so x plus y must give 90 degrees. Or this angle x plus y, y is also this, right? If this is y, this is also y, or x plus y is 90 degrees. Or we can say angle BAC, as I have shown you, plus angle CBA, which is not actually this, it is CAD actually, right? Angle BAC plus angle CAD, so this will be angle CAD. Angle BAC plus angle CAD is 90 degrees, right? Because both of them, this angle and this angle, were y. So how can we find angle B? How can we find angle B? We know that this angle is 90 degrees, right? This angle is 90 degrees. And how can we find angle B? We can find angle B, as you can see, AD and BC are parallel, and now we consider AB as the transversal. And you can see these two angles are actually co-interior angles, right? Angle BAD and angle CBA are co-interior angles. Therefore, they must also add up to 180 degrees. And if we subtract the value of one of the angles from 180 degrees, we get the value of the other angle. So let us do 180 degrees minus the value of this angle. Therefore, we can get here angle B equals 180 degree minus the angle which we have talked about, the angle BAD. The sum is shown here, angle BAD. So we get 180 degrees minus 90 degrees, and we can tell angle B is 90 degrees, right? Angle B comes out to be 90 degrees. And therefore you can see here ABCD is a parallelogram with an angle 90 degrees, where B is 90 degrees, A is also 90 degrees, and in a parallelogram the opposite angles are equal, right? If angle A is 90 degrees, angle C must also be 90 degrees. If angle B is 90 degrees, angle D must also be 90 degrees. And therefore you have seen that we have finally found out ABCD is a parallelogram with all the angles 90 degrees. Therefore we can say ABCD is actually a rectangle, right? Therefore we can say here ABCD is actually a rectangle. So what have we done here? We have first found out the equation based on the angle bisectors, right? We have named the angle bisectors with variables so that we don't need to write the names over and over again. And what have we done? First we have proved that ABCD is a parallelogram, and then we have found out the equations using co-interior angles which add up to 180 degrees, and found out that the measure of one of the angle is 90 degrees, and with that we have found out the measure of the other angle also to be 90 degrees. And using the laws for parallelograms, using the theorems of parallelogram which we had learnt in our earlier class, we have shown here that the parallelogram is actually a rectangle. So we have proved that the quadrilateral formed by the angle bisectors of the given figure is actually a rectangle. And also there is an alternative method to find out. Let's look at it. Alternatively, in a similar way, you can find out that this angle is 90 degrees, right? And obviously you can find out angle B is 90 degrees, right? And in a similar process, you can go on using the rule for co-interior angles. You can go on using the rule for co-interior angles. First you take A and B as the co-interior angle, B and C as the co-interior angle, then C and D as the co-interior angles, and you can proceed in a similar fashion to get all the angles to be 90 degrees. You can see here, by doing this we have got angle BCD equals 90 degrees, right? Angle D also equals 90 degrees, and here we have got angle B also equals 90 degrees, and initially we had got this angle was 90 degrees, right? Finally, we can say that all the angles of ABCD are 90 degrees, right? Hence it is a rectangle, and here we need not even prove that it is a parallelogram. If all the angles are 90 degrees, obviously all the opposite sides would be parallel to each other, right? Because if two sides are perpendicular to each other, then the sides opposite to them will always be at the same perpendicular distance forever, right? So in alternative method, by finding out that the sides using the parallel sides and finding out the angles, we have proved that the figure given here, the figure formed by the angle bisectors, is actually a rectangle. So let us look at another condition for a quadrilateral to be a parallelogram. So this statement has been put in the form of a theorem. A quadrilateral is a parallelogram if a pair of opposite sides is equal and parallel. So if only one pair of sides are equal and also parallel, even then we can say that the closed figure formed will be a parallelogram, right? We are considering here only one pair of parallel and equal sides, right? We are considering, in the given figure, we are considering AB parallel to CD and also AB equal to CD, and we need not know any other information about AD or BC. So let us verify this given theorem, whether this holds or not. So you can see here we are given AB equal to CD, right? And AB is also parallel to CD. So let us consider the two triangles, triangle ABC and triangle CDA. So we are considering these two triangles. And in these two triangles, we see that AB is equal to DC, right? AB is equal to DC, and angle BAC, which is this angle, is equal to angle DCA, which is this angle, right? And why are they equal? They are alternate angles where AB is parallel to CD and AC is the transversal. So you can see here AC is common for both the triangles, so they must be equal to each other, right? So you can see we have got the three criteria for showing that these two triangles are congruent to each other, right? Or these two triangles are exactly alike. And by which rule? Side angle side rule, right? SAS rule. So we have proved that angle ABC, this triangle, is congruent to CDA, which is this triangle, right? So you can see here, by CPCT we can easily find out angle ACB, which is this one, angle ACB, and angle CAD. CAD is this one. These two angles are also equal by CPCT, right? Because by the pattern in which they are overlapping onto each other by the naming shown here. A overlaps on C, B overlaps on D, and C overlaps on A, right? If the two triangles are separated out. So by CPCT we get angle ACB is equal to angle CAD. Now you can see if these two angles are equal, they are acting as alternate angles only, right? That means CA is the transversal and AD and BC must be the parallel sides because the alternate angles are equal, right? These are alternate angles, so AD must be parallel to BC. So we have got these two sides were parallel, it was initially given, and we have found out these two sides are also parallel to each other, right? These two sides are also parallel to each other. And in which figure do we find the opposite pairs of side parallel? Obviously it is a parallelogram. So we have shown that the theorem about the condition for being a parallelogram is true, right? Thus ABCD we have got as a parallelogram. So let us solve one question using whatever we have learned. Now this question has more than one parts, right? So we will look at one part at a time so that we get to know how we can use these concepts in each question. ABCD is a parallelogram in which P and Q are the midpoints. You can see here P and Q are the midpoints of the sides AB and CD respectively. If AQ intersects DP at S, you can see here, and BQ, which is here, BQ intersects CP at R, we have to show that APCQ, which is using the vertex A, P, C and Q, the quadrilateral formed by these four vertices is a parallelogram. We have to show that. Now let us look into the figure more closely. Now from the figure you have seen AB equals DC, AB equals DC, right? By the rule of parallelogram, opposite sides are equal and parallel. So half of AB must be equal to half of DC because they are of the same length. So what is half of AB? Half of AB is nothing but AP or PB, right? And half of DC is DQ or QC. And all these parts must be equal, right? Because they are half of the same length. So DQ must be equal to QC, must be equal to AP, which must be equal to PB, and which is nothing but half the length of the side AB or the side DC. So we are keeping this aside because we will need this in our following slides. So let us consider the quadrilateral we are concerned with, APCQ. So we have seen that AP is parallel to QC, right? Because ABCD is a parallelogram, opposite sides must be parallel. And also AP was equal to QC, right? AP was equal to QC. Or you can say AP is parallel to QC and also AP is equal to QC because both of them are half of the same length. Now we can see here one pair of opposite sides are parallel and equal. So what can the figure be? Obviously by the theorem we have learnt now, APCQ must be a parallelogram, right? So you can see here how we can use a theorem to simplify one question, and it can be solved in mostly two steps, right? We have just got AP parallel to CQ is our first step and AP equal to CQ was our second step, and yes, we have used the theorem effectively and we have found out that APCQ is actually a parallelogram. So let us use this once again to find out the solution for the second part. The second part says DPBQ must be a parallelogram. So let us find out which one is it. DPBQ. So the quadrilateral formed by this must be a parallelogram. Let us see if we can find out that too. Let us consider the quadrilateral DPBQ, and here also DQ is parallel to PB, right? DQ is parallel to PB, as ABCD is a parallelogram, and also DQ is also equal to PB, right? Because both of them are half of one side. So here also we find that one pair of opposite sides are parallel and equal. Therefore we can easily say, by using the theorem, we can say DPBQ is a parallelogram, right? So we have easily solved the first and the second part using the theorem, the condition we have learned for a quadrilateral to be a parallelogram, that is, opposite sides must be equal and parallel. So let us see how to find out the third part, PSQR. Let us see which one is it. P, S, Q and R. So you can see, so we have to encircle R. Let us encircle R correctly. Okay, so this is the quadrilateral we are concerned with, and we will use what we have got from our earlier parts, and we will use them in this question. So let us use them effectively. We have got AQ parallel to PC, because it was a parallelogram, right? So AQ must be parallel to PC, and also DP must be parallel to QB, right? From the parallelogram APCQ, we have got AQ parallel to PC, and from the parallelogram DPBQ, which is the second part, we have got DP parallel to QB, right? We are talking about the longer sets of parallel lines for the two quadrilaterals we had talked in our first and second part. So you can see, if AQ is parallel to PC, then obviously the parts of them, which is SQ, must be parallel to PR, right? And also from the quadrilateral DQBP, we can get SP is parallel to QR, right? A part of them must also be parallel to each other, right? After considering this quadrilateral, the inside quadrilateral, we have seen that SP was parallel to QR, as DP was parallel to QB, and SQ was parallel to PR, as AQ was parallel to PC, right? And so we have got the opposite sides, we have got the opposite pair of sides parallel to each other, and obviously it must be a parallelogram, because both the pair of opposite sides are parallel to each other. So we have proved PSQR is also a parallelogram by simply using what we had obtained from the first and second part. So in this class we had learnt about parallelogram. We have completed this topic, and we have learnt one more condition for a quadrilateral to be a parallelogram, right? Which is the one pair of opposite sides must be equal and also parallel. And see you next time.